maybe housekeeping type things or just things to go over. Okay. First, I'll say this. Believe it or not, the stack's getting smaller. Okay. I probably will grow some today, but I finally, on Friday, just about completely finished the schedule for spring. I thought I had, on the way home, I thought of one or two more things I might need to do. I got those taken care of. And then since then, I've had a couple of emails and phone calls, can we do this? So I've got a few minor changes, but my schedule time is finally finished. Well, at least for spring. I still have to do summer, but that can wait. So I have gotten back to grading finally. And I've got all of your first labs graded. Now, they're not in Blackboard yet, okay? I don't have them in Blackboard, but I do have them graded. I've got all your first tests graded. So I've got those two big chunks out of the way, and I'm still getting in more, okay? That's good. I thought I would have, pretty close to 3 hours a day to work on it, but I had just a series of students coming in for advising and had a few other things I had to take care of. So I only got basically your test graded. Now, let me say this about the labs. First lab, I'm still missing 1, 2, 3, 4 labs. Okay? Make it 5. 5 labs. Okay? Please get those in so I can get them back to you. I don't want to carry these around forever. The first test y'all are doing much better on. I'm only missing 2. Okay? And both of them are here today, and please get those done as soon as you can. Okay? Okay, so I can get those back to you. Now, the rest of the labs I'm still grading, and hopefully I only have about 2 hours, maybe even 1 hour of office hours tomorrow, so I'm not going to get that much done tomorrow. I've got some things to do for that class, so I probably won't get any of your stuff done. Thursday, however, I should have another pretty good chunk of time to get quite a bit more graded then. I've been grading at home, too, when I have a chance, but that isn't always consistent, the time I have. Now, that's looking behind of how I'm trying to catch up. Now, let's look at today. Today, the lab, and we aren't ready for the lab yet because we've got to cover a little more material, but I don't think it'll be too long before we'll be ready for the lab. Now, normally it would be at the last 2 hours, 5:45 to 7:45. Today is a very short lab, okay? So actually it should not take us that long, but at 5:45, a biology class has just gotten started down there. They start at 5:30. So what we need to do, and the lab I need to use because the equipment's so heavy, I didn't want to lug it up to one of these labs and then have to lug it back down. So what I've decided to do, there is a biology class in that room right now. That's fine. We're not ready for the thing either. Anyway, but as soon as we finish the material that's covered on this lab, then we're going to go down and do the lab in the middle. And that way we'll be through before the next class comes in there. The next class, I think, comes in at 5:30. So if we can get the lab knocked out, and it's not, like I said, it's not going to take us long. The actual physical measurements are relatively short, okay? Then there's some calculations to be done. We can come back to the classroom and do the calculations, okay? So what we'll do is start on the lecture today, get what we can covered, get as much as we can, need to cover to hit the lab. And then once we're through with that, I'll mark the time so we'll know how much lecture time we covered. Then we will go down and do the lab, because we usually do that at the end, and when you finish, you get to go home. Well, not today because we're going to take it. But then when we come back up and you finish the lab, and then we get started on lecture again, I'll start the clock on our 2.5 hours again, okay? So, and then when that 2.5 hours is through, we'll stop and go home. Is that okay? All right. Rather than being the 2 hours at the end for the lab, we'll have those 2 hours in the middle, but I'm almost certain it's not going to take you 2 hours. then rather than extend the class, I'll give you credit for those 2 hours, and we'll just end the class a little early. Okay? You okay with that? Okay. You can live with it. Okay. Then that's how we'll handle today. Now, when we come back and finish, I'm pretty sure we will finish the chapter today. And if we do finish the chapter, that means on Thursday. Okay, let me tell you a little bit about Thursday too. Okay, there's a faculty meeting Thursday at 2:30, but it's over here in Ethel Hall Auditorium. So I'm going to be there. So if you were planning to come by and make up something, you'd better be by before 2:30, because in fact a little bit before that, because probably I'll leave to go about 2:15 to go over to Ethel Hall. So because I won't be in the office from about 2:15 until close to 3:15. I'll leave the meeting before 3:15, probably 3:10, to come back over here. So I may be a few minutes late getting back here. Hopefully not. But if I am, don't go anywhere. I'll be here. I'm leaving the faculty meeting early just so we can be together. Okay, just for your benefit. So I will be here, though I may be running just a tad late. So that's Thursday. But we should have a full class. But now, what will we be doing on Thursday? If we do finish the chapter today, which I think we should, that means at least the test is going to be Thursday, the last 30 minutes. Okay? That's if we finish the chapter today. If we don't finish the chapter today, that means on Thursday, it's probably going to be pretty close to a marathon. It will go at least 2.5 hours into finishing this chapter and starting the next one. If at that 2.5 hours we've gotten enough covered to do a new lab, then we'll do the first lab for chapter 4. Okay, I think we should be able to. Now, if we finish this chapter today, and maybe even get started a little bit on chapter 4, then we only have, if in 2 hours we cover enough, on Thursday, we cover enough material for the first lab, then we'll stop and do the lab, and then the last 30 minutes will be the test. Okay? So that's how it's looking like it's going to pan out. So let's get going now. And this is where we left off last time. So let me get from current slide. And we were talking about potential energy. Someone give me a quick description of what potential energy is. No, that's kinetic energy. Position is right there. The energy associated with position. Okay, we talked about this, how you need a reference height. We'll be doing that in today's lab. That work can change the potential energy. I think we talked about that. Kinetic energy can change into potential energy, and vice versa. We'll be doing that in lab today. Okay? Now, this is where I think we left off last time. If we had a 4-story building like this, and we're on the top floor, and had a book, and was hanging out the window, what would be the potential energy of the book? This goes to here. Okay? You need a reference height. If it's the floor of that 4th floor, then that would be the potential energy. That would be the height. MGH. That height. If it's the floor of that 4th floor room. So if you're holding the book above the floor, on the 4th floor, that would be its potential energy. If that's your reference position. But if you go to the window and hold it out, then the reference position should be down here on ground level. But if you'd already established that as your reference level, then this would be its positive potential energy. This would be negative because you're below your reference level. So that's what they mean. You have to identify where your reference height is, what the reference height is being measured from, what the position is. And my recommendation, I said this last time, is to pick the value that's as low as that object can go in the context of that problem. That's what we'll be doing in today's lab. Okay? So you see, potential energy can be positive. Most of the time it is. It can be negative if your reference level is above the final position. Okay? It's sort of crazy for that to be a negative potential energy, but it can be. Okay? That means it takes work to get it back up to the reference position. Most of the time the reference position is as low as it can go, so you've used all the work to get there. Does that make sense? By the way, the formula again is, now this is gravitational potential energy. I wish they wouldn't just call it PE, I call it GPE, and this would be mgh, where h is measured above the reference position wherever you set it. So if it's down here, this is the new height. Now that's not the same height as this height. I wish they'd used a different letter, a different color or something, but that's a negative mgh because you're below the reference position. Does that make sense? All right. Now, before we move to kinetic energy. Yes? Okay, with the building there? Okay. Okay. And by the way, all the slides are out there on Blackboard too, so you can get them there as well. All right, before we move on, I'm going to back up one so we can have room to write here, if I can get my pen out. Okay, we're ready for example 3.5, and then we'll do 3.6. What is the potential energy, and I'm going to assume this is, let me get my pen activated. This is gravitational potential energy. That's what we're looking for. That's the question. Excuse me. That's the question. What is the potential energy or gravitational potential energy of a, I've got to sneeze, sorry.
Bless you.
Y'all awake? Okay. Of a 2.14 kilogram book. What's that a measure of? That's your mass. Okay? That is on a bookshelf 1 meter above the floor. 1.0 meter above the floor. What that'd be a measure of? That's your height. Okay? If the floor is your zero reference level, which we will assume in this problem it is. So what's the gravitational potential energy? What's its formula? Okay, that's part of it. What's the formula? mgh. Your mass is 2.14 kilograms. Your g is 9.8 meters per second squared. And your height is 1.0 meters. Okay? And when you multiply those together, someone with a calculator, 2.14 times 9.8. Okay. Yeah. 21 on the nose? About 21 what units? Joules. Okay. Kilogram, meter square per second square, that indeed is a joule. All right.
We were trying to get specific. It's 20.97.
Second?
It was 20.972.
Okay, 20.97. Okay, good point. Okay, but look, this has 3 significant digits. That only has 2. 9.8 could be 2 or 3. We have to go with the smallest number of significant digits. So we round to we count over 2, look to our right. It was greater, so we moved it up. Okay, 21 joules. Okay. Was there a question? Okay. Example 3.6, how much work? This time we're looking for work. Excuse me. Okay. All right. How much work can a 5 kilogram mass, there they just told us what it was, 5.00 kilogram, that's the mass, okay, do if it is 5.00 meters above the ground? What would that be? Your height. Okay? And Justin's here. All right. All right. All right. So how much work can it do? Well, it's going to come back in a minute. Okay, there it is. What is work? Is what?
Hour into time.
I can't.
Hour into time.
Okay, we don't have power in this problem. You're right. Work is power times time. But what's another definition for work? What's another definition for work? Say again?
I said I don't know because I wasn't here last class.
Okay, we had it earlier in this chapter. Last chapter. Didn't we? Yeah. No, earlier in this chapter. What is work? Yes, force times the displacement. F times D. Okay? Where our force here is what?
5.
That's the mass. What's our force? What is a force compared to mass? Newton's second law. Yes, mass times acceleration, so that would be mg, there's the force, times the height, which is your displacement. So what would it be? 5.00 kilograms times 9.8 meters per second squared times 5.00 meters. Okay, sorry, run out of room. And that would be 25 times 9.8. What would that be? $25 times 9.8.
It says 150 in the book, but when you multiply it on the calculator, it says 245.
Say this again.
It says 250 in the book, but when you do it on the calculator, it says 245.
Okay, what did you say it is? 245?
On the calculator,
Okay.
the book says 250.
25 times 9.8, you say 245? Is that what you got?
Yes.
Yeah. And that would be what units? Joules, or kilogram meter squared per second squared, or Newton meters if you wanted to split it that way. But here again, look, 9.8 only has 2 significant digits. So what you do, what you do is count 2 significant digits, look to your right, that's a 5, that's 5 or more, so you up that by 1, and you make that 250 joules. So yeah, it's just the way they round it off. Okay? And that's because they only had 2 significant digits in the 9.8. Even though you had 3 in kilograms and 3 in height, you only had 2 in 9.8. All right, good deal. Any questions on that? All right, then there is a concepts applied, and that's basically the lab we did last time, or the time before. Yeah, last time, I guess, when y'all ran the steps. Was that last time? Last Thursday, okay. So that's the lab we did, so you've already done that one. So now we're ready. Any questions on gravitational potential energy? Okay. Now we're ready to move to kinetic energy. What did we say kinetic energy was? It's the energy associated with motion, right there. Okay. Now, just like we saw from, and here's what I meant to say. Let's go back. Notice the gravitational potential energy and the work formulas are almost identical in some circumstances. And that's because increasing something's gravitational potential energy is the same as giving it the potential to do work. And that's how that question was asked. How much work can that mass do? In other words, if you give it that much gravitational potential energy, that's how much work the mass can do. Especially if I dropped it from 5 meters high, 5 kilograms, onto your foot, you would feel how much work that could do. I'm not going to. Okay, I can't reach up to 5 meters. Okay. Oh, that's not the reason. Okay. So kinetic energy also results from work or a change in potential energy. Remember, all these units are the same. They're all joules. They all are related to each other. Kinetic energy, potential energy, and work. Okay? Now, the formula for kinetic energy is this one. Kinetic energy is 1/2 the mass times velocity squared. I don't know if you remember or not, but back in, I think, the first chapter, I mentioned whenever the main variable is squared, it's usually preceded by 2 in the denominator. Okay? And here we have Stefani. Good deal. All right, so we're just missing Gary and Colton, Mac, Zachary, Kevin, Steve. No, I'm sorry, we got Steve. Brian and Raina. Okay. All right. So here's the formula for kinetic energy. Notice what is kinetic energy? What's its definition? Energy associated with motion. If something's moving, it has to have a velocity. So there we have the velocity in here. But it's not just the velocity. It's the velocity squared. Actually, it's the speed squared. Actually, it's velocity times velocity, but that is a dot product, so that becomes speed squared. Now, here's the key, folks. Does that look a lot like some other formula we had fairly recently? Which one? Say again? Potential energy didn't have velocity in it.
No.
What other formula did we?
Centripetal.
The what?
Centripetal. The circle one.
Centripetal.
Say again? Okay. Now that has velocity in it. You're absolutely right. Okay. But as another, and that was what we're talking about there was the acceleration or the force of that. But I'm thinking of another sort of motion-related thing, and centripetal does have that. One more that only had these two variables in it. That should give it away. Say again? No. Mass and velocity. What is mass times velocity? Oh, how soon we forget. Say again? No. Time rate of change of this is force. Momentum, exactly. So kinetic energy is a lot like momentum, only different. Here's one difference. Momentum is a vector quantity, kinetic energy a scalar quantity. Momentum depends on velocity to the first power, and it is velocity. Kinetic energy depends on speed to the second power. Okay? So what this means is if you double your speed or velocity, you quadruple your kinetic energy. That's why when you're driving down the road, if you're driving at 30 miles per hour, you don't have to be as far behind the vehicle in front of you safely as if you're driving at 60 miles an hour. Why? Your energy you have, the kinetic energy, isn't just doubled when you double your speed. It goes up by 4 times. And what that means, you have to supply 4 times the energy to get yourself to stop. So you should not just double your distance, you should quadruple the distance between vehicles. Very few people do that. And quite often you have pretty major collisions on the interstate because people don't allow enough stopping distance. It's called tailgating in the other sense, okay? And it's not the good sense, okay? Now, that's all they say about kinetic energy. Whoa, did they ever cheat us on that one? So let's go back and let's do the examples on kinetic energy. All right, example 3.7. Boy, did they ever cheat us, okay? Before we do that, if you got your book, please turn to it. If you don't, I can't draw this picture, but I'll show it to you. Okay. You may have done this in your life. I imagine many of you have. Bowling. Let's think about the energy transfers that go about here. Okay? First, when you're going to send the ball down, what's one of the first things you do to the ball? You raise it up. When you raise it up, you're giving that ball what kind of energy? Which kind? I couldn't hear. I heard energy, right? Potential energy, the energy of position, raising it up. So that the work you did was FGD, which is the weight of the ball and how far you lifted it, but it's also how much potential energy you gave it. So then when you swing it down, you're releasing that potential energy, plus any that you might, with the force that you give to it, that would also give it more energy. When it's on the floor and rolling, though, what kind of energy does it have? Second? Kinetic energy, because it's only the energy of motion. We'll count the floor there as being our zero reference frame. So it's not got any more potential energy, but it is kinetic energy. But up here, when you had it right at the peak, what kinetic energy did it have? None, exactly, because it wasn't moving. Right when you had it at the top, before you release it, that would have zero kinetic energy. So all the potential you gave it there, plus any work you did on it, pushing it down, that would be the total kinetic energy here. Then, when it hits the pins, if yours does, mine usually didn't, when you do that, it gives that kinetic energy to the various pins, and they use up not much of that, and that does work on the pins. Boy, that's work holding it up there. Or is it? No, it's not changing position any, so it's not work. It felt like it though. Okay. So let's go to example 3.7. And this has to do with what I was just talking about. A 7-kilogram bowling ball. What's that a measure of? That's the mass of the bowling ball. Okay? Is moving in a bowling lane with a velocity of 5 meters per second. So the velocity is 5.00 meters per second. What is the kinetic energy of the ball? That's your question. And what is kinetic energy? 1/2 mv squared. And that would be 1/2 of 7.00 kilograms times 5.00 meters per second. But what do we do with that? Square it. Okay, so that would be 1/2 of 7.00 kilograms. And what is 5 squared? 25, and technically you could put 25.0. What units? Meter square per second square. You must also square the units as well. Okay? Now, probably need a calculator for this one. 7 times 25 is going to be 175, I believe. And half of that would be 37.5. So that's 87. That's what I was going to say. That's not 30. 87.5. What units? Joules. Kilogram, meter square per second squared, just like before. 87.5 joules. Okay? Does that make sense? This way we kept all three, because you see 1/2 is a pure number. This is as many digits as you want. 0.500000, as many as you want. That had 3, that had 3, this had 3, that had 3. Everything had 3, so you could round that to 3 significant digits. Okay? And it came out exactly that. All right, let's do 3.8. So let me erase this one. Everybody got it? Or you want me to keep it a little bit longer? Got it? Everybody? Okay. So let me erase this and go to 3.8. A 100 kilogram football player. What is that a measure of? That's the mass of the football player. Now, does anyone have an estimate what his weight is?
980.
No, okay. Oh, yeah, you're going to give it to me in newtons, okay? That would have been fine. How about in pounds? Does anyone know approximately what the equivalent weight in pounds 100 kilograms is? What they used to tell you in math books when they were teaching changing units, they say a pound is, let's see how they'll say that. No, a kilogram is 2.2 pounds. It's not. They're measuring mass there, but you can use that as a ballpark. So he's a 220-pound football player, okay, approximately, okay? So 100 kilogram football player is moving with a velocity of 6.0 meters per second. So his velocity is 6.0 meters per second. And he tackles a stationary quarterback. What does that mean? The quarterback's going to feel it pretty good, right? Because he's not moving. How much work was done on the quarterback by the 100 kilogram football player? Well, guess what? After he hits them, they come to a rest. So all of his, what kind of energy did it have when he was moving? Kinetic energy. And once he smashes into the quarterback, it goes, that's just expended in work. So all that energy goes to work. So let's see how much it is. How much kinetic energy did he have? Help me. What's the formula?
2600.
Say again?
1800.
Okay, but how'd you get that? 1/2 of mv squared. That's 1/2 of 100 kilograms times 6.0 meters per second squared. So 1/2 of 100 is 50, so I'm just going to put 50. I'll keep the units kilograms times, what's 6 squared? 36, and we'll leave it that many digits. What units? Meters squared per second squared, and that gives you basically 1/2 of that, 18, as you said before, 1,800 joules. Kilogram meter squared per second squared. Okay? Yes? Yeah, I divided 2 into 100 to make it 50. You can do that anytime. The last one I didn't do that because it was 2 into 7 and 5 squared. All odd numbers, so I couldn't do it easily. So I multiplied them out and then took 1/2 of it. But when it can divide out early, I just go and do it so I don't have to haul it around. Okay. Remember, multiplication is commutative and associative. Yes?
So, how we know that we don't have to find work?
What's that again?
How can we know that we don't have to find work?
Okay, because we know that all of the kinetic energy was expended somewhere. And where does it go? He did work on the quarterback. In other words, bruised them up pretty good. Okay? Ask, what was the LSU quarterback's name? I don't remember. He got bruised up pretty badly last Saturday night. Poor guy. Okay. Anyway. That's kinetic energy. Now, next topic is energy flow. Now, this is an old concept here. It really goes back to the concept of heat, which we're going to cover in the next chapter. But in the old days, they thought heat specifically, or any type of energy, was actually some ephemeral fluid with no mass, you can't see it, but it flowed. It was a fluid, so it had the flow. So we started using these terms like energy flow. Well, there's no physical thing there to flow, but they thought there was, okay? And so we still use that terminology. What is energy flow? Well, energy can do work as energy against inertia, okay? Energy, or work against gravity, work against friction, work against shape, work against any combination of more things in these here. Any of you ever experienced work against inertia? I'm almost guarantee you some of you have had to push off a car to jump start it sometime in your lifetime, have you? Yeah, okay. You were doing work against inertia. It wasn't wanting to move, okay? It was sitting there and you were having to get it to move. That was work against inertia. They'll show other examples. Work against gravity. Any of you ever done that? How? Picking up anything, a box or anything else, you're doing work against gravity. Work against friction. Any of you ever done that? Sliding anything across the floor that's resisting you, that's friction. Work against shape. Any of you ever done that? A spring, that's certainly one. I'll give you another example of one, not too pleasant of one, that I experienced. When I was in grad school in Nebraska, there were a group of us that decided to have there was a league for co-ed volleyball. So we decided to, and we had a real tall gal in our group, and she had played before, so we thought, yes, we'll do this. And she had a good friend who was an excellent setter, okay? They had played together in high school. We said, yes, okay, we will go to this. Did I tell this story last time? I thought I did. So some of you have heard it before, but I'll go over it again. So and we had some guys that were okay, So we joined the league, and one of the nights we got there, and this other team had a real tall gal, and just looking at them warming up, you could tell she had played a lot of volleyball before, and she had a friend who was an excellent setter. Okay, you're a setter, right? Okay, you know how important that is. Okay, so and when you're playing volleyball, you cycle around the court. So at some point, always you're going to be against every other person that's on the other team, unless there's a substitution or something. So I knew at some point I was going to be right across the net from this rocket gal, And sure enough, when it came that time, we either served to them, I imagine we served to them, and it went wherever it went, and they got it to the setter, and she set it up just perfectly for this gal. And all I could do was get up and go as high as I can, make as much surface area as I could to see if I could block what I knew was coming. Okay, and in the process of doing that, her spike came down at a tremendous angle, missing my hands completely, hitting me square in the face. Now, you may think a volleyball is soft. Is it? No. It's really pumped full of air. I mean, tightly pumped full of air. And that ball is anything but soft. I mean, it's not like a baseball or softball or, a tennis ball, golf ball, but it's still plenty there. And that ball came down with such force that I felt the ball touch each ear at the same time. My face had done work against that volleyball in deforming it big time, work against its shape. All I saw was Wilson, no, I didn't really see it, my eyes were closed. But anyway, that was work against shape. I prefer the spring, but we'll do that. Or any other examples. So here's some examples. Pushing off a car, you're doing work against inertia. Or, how about this one? Anyone ever throw a baseball to you? Okay? Did you catch it? You worked against its inertia. Its inertia was coming at you this way. You changed its motion if you caught it. Okay? Or even if you didn't, if you deflected it. That is also work against inertia. Okay? Or if you swung at a baseball or a golf ball or any other kind of ball and changed its motion, you did it. Work against gravity is lifting something, okay? Just like you described, lifting a box, a book, or whatever. Work against friction, pushing anything across an uneven surface that is hard to move, you're doing work against friction. Your force is this way, your displacement is this way, the friction's that way. That's the force against friction. Okay? and then they get the spring. And y'all know that in your cars, there's some pretty heavy-duty springs there. Do they still have mostly coil springs, or are they more leaf springs? Leaf springs are on the larger vehicles, right? Say again? It depends, but a lot of times they're coil springs still, right? And but that's, anytime you hit a bump, the spring is doing work against that, the force of the bump, or vice versa. Okay, you just press it and it comes back. Okay, now we won't get to that. There was another follow-up question. Okay, that's all they have pretty much on the beginning of energy flow. But a subtopic of that is energy forms. Now here's an important one. We'll be using this in today's lab. The definition of mechanical energy is the sum of kinetic plus potential energies. Okay? The definition of mechanical energy is the sum of the kinetic plus potential energies. Now remember, potential energies, there could be many of them. Spring potential energy, also called elastic potential energy, gravitational potential energy, chemical potential energy. There's a bunch of them, okay? The sum of your kinetic energy plus your various potential energies would be your mechanical energy. You have others like electrical energy, and we'll talk about this in 2 chapters away. That would be charges, currents, and things like that. Chemical energy, I just mentioned, energy involved with chemical reactions. Some going on right out there, outside of our window. Right now, those little green leaves. Now, once they change color, they're not doing this much anymore. Those little green leaves out there, when they catch that sunlight, they're converting carbon dioxide and water into simple sugars. That's a chemical reaction that's going on there, and the energy is stored in those simple sugars. Okay? If they go on to make a fruit or something, and later we eat the fruit, we can convert that energy back into energy of motion or other types of energy. What did I say they were using? The light from the sun. That's radiant energy. Okay? That's a form of electromagnetic energy. Visible light is one form of that. It's a very small part of the full spectrum of radiant energy coming from the sun. But thank goodness that's most of what our atmosphere allows through. We are so fortunate to have the atmosphere we do that only allows, by and large, that little portion of the full spectrum of the radiant energy coming from the sun. That high energy radiation that comes, like the gamma radiation, the cosmic radiation, the X radiation, all that stuff, our atmosphere blocks really, really well. Thank you very much. Even ultraviolet radiation, okay? Doesn't block all of that, but it blocks most of it, okay? What's some evidence that some ultraviolet radiation gets through? Second? People get skin cancers. That's from ultraviolet radiation, too much of it, hitting the same area of your skin too many times, your body trying to fight it off, after a while it loses.
Australia in summer.
Second?
Australia in summer.
Australia in the summers? I bet you it's pretty hot.
They don't have ozone layer as much compared to the other countries.
They what?
They don't have ozone layer
Oh,
as much compared to other countries.
okay. Yeah, I know Australia being, they have a disadvantage that we don't have. Do you know what day the Earth receives the greatest amount of solar energy? What day of the year? Any more than others? Actually, the Earth's orbit is not circular. It's slightly elliptic, meaning it's closer to the sun at some time, further from the sun at others. The day of the year when it's closest to the sun is right around January the 3rd or 4th, right in the middle of our winter. So therefore, our temperatures get moderated ever so slightly. It's not a big deal. But guess what? In the southern hemisphere, that's smack dab in the middle of their summertime, they're also closest to the sun, so they get a double whammy on extra radiation coming in. So yeah, Australia wouldn't be at all surprised if they don't have a bit more of a problem than we do. Another thing that's a result of ultraviolet radiation, I bet you some of you, either parents or more likely grandparents, have had this cataract removed. Any of you? You probably wouldn't even know. I've had one. My right eye had to have a cataract removed. I think my left eye is almost at that point too. I get really tired reading these days, and I think that's the reason. Okay? But ultraviolet radiation does that. Also for older people, especially those who look like think of a good illustration. Lots of wrinkles.
Beef jerky.
Second?
I said beef jerky. No, I said beef jerky.
Beef jerky, possibly. Okay? That's from skin being damaged by ultraviolet radiation. So these sun worshippers who go out and get the great tans, they're going to have the prune face. That's what I was trying to think of. Okay? When they're older. Okay. So radiant energy. Thank goodness our atmosphere blocks out most of that dangerous radiation. Nuclear energy. The energy involved in nucleus and nuclear reactions. That's what's going on in the sun, producing all that harmful and not as harmful radiation is nuclear energy coming from the sun. Now we've harnessed that here on Earth, and we have nuclear power plants, either producing electricity, powering ships, other things like that. We use nuclear power for that. Nuclear energy, I guess I should be saying. So all different types of energy forms. The one we'll be dealing mostly with is mechanical energy, which is the sum of kinetic and potential. All right. Now, what time is it?
4:08.
Second?
4:08.
4:08. Okay. Let's go to 4:15. That will put us exactly 1 hour into the class. And at 4:15, we will pause, go down and do the lab, and at least get the data from the lab. Then we'll come back up from the you'll be doing some calculations down there. So take your calculators, and we will, after we do the lab, we'll come up and finish the lab here. And then when you're through with that, we'll start the clock again and do just an hour and 30 minutes after we get back up here. Is that okay? And will y'all be okay leaving a little early? You will? Okay. Whew, I was afraid y'all were going to be upset. And report me to the dean that I'll let you go too early tonight. Okay, today. All right. So let's talk. Oh, we need to be doing this anyway. Energy, in fact, we may go past 4:15. I didn't realize that's this section. Energy conversion. Any form of energy can be converted to any other form. At least they say that. There's one form that is hard to convert to other forms, and that's the heat that's left over from residual heat from friction. It's really hard to convert that back to any other useful form. But technically it can be. Energy flows from one form to another in natural processes. And the example of this they give is the pendulum. Well, here's the guy with the bowling ball, finally. Several pages later, they finally use this one. Okay, let's think of the energy conversion. Okay, number one, he's eaten that day, right? Probably had a fair amount of carbs, maybe a few fats, I'm sure. And in so doing, he's got energy in his body, and he picks up the bowling ball. That's doing work on the bowling ball, lifting it behind him. That's doing work on the bowling ball, and then swings it down the court. That's giving more energy to it. So he's giving it potential energy, giving it kinetic energy. He's doing that. But once it leaves his hand, he's not contributing a bit more energy to that bowling ball. From that point on, all it has is kinetic energy. Not increasing its elevation, that lane should be perfectly flat. Okay? And then when it hits the pins, it transfers that kinetic energy into banging the pins all around. Okay? Making a lot of noise. That's the type of energy. Okay? Sound energy. Okay? And it releases and changes that energy in the distance that it has there, doing work on the pins. So that's one type of energy conversion. The food the guy ate stored chemical energy into the energy of contracting his muscles and that kind of stuff, giving that kinetic energy, potential energy to the ball, then kinetic energy to the ball, and then the ball's kinetic energy does work on the pins. The other is the pendulum. This is what we'll be doing in today's lab. What we're going to do is raise the pendulum up to a certain height, giving that much what kind of energy? Potential, gravitational potential energy. And at that top height, when it's not moving, all the energy is in gravitational potential energy. Then when you release it from rest, release it, not throw it, release it, then you allow some of that potential energy to lose potential energy as it loses height, but as it does that, it gains kinetic energy as it picks up speed. And it picks up speed all the way down in this arc until at the bottom, it can't go any lower than that, so it has zero potential energy there. All of its energy that was up here as potential energy is now kinetic energy at the bottom. Okay? Then it keeps on moving. How high does it go over here? That same height. Okay? Now, if there is any friction loss or air resistance stuff, it may not be quite as high, but by and large, it'll go to the same height. Why can't it go any higher? Yes, that's all the potential energy it has. If all that gets converted back to potential, it can't go any higher. Okay? And then it stops momentarily and goes back the other way. And goes this pattern over and over again. Potential, no kinetic, kinetic, no potential, potential, no kinetic, back and forth, back and forth. That's the pendulum. Are you getting sleep? Never mind. Okay. Here is the key here. Even though it's changing potential energy constantly, changing kinetic energy constantly, what is not changing? What's that?
The reference.
Can't hear.
Reference.
One more time.
Reference.
Reference.
Huh?
Reference.
Okay, the reference level is down here. But what kind of energy is not changing? Hint. Mechanical energy, exactly. The mechanical energy stays the same because it's the sum of potential and kinetic, potential and kinetic, potential and kinetic. That's always the same. Mechanical energy is conserved. Okay? And now we move to energy conservation. But before we do, let's do a couple of examples. Okay? 3.9. Okay, let me back up right here and do 3.9. This is on page 75. A 1 kilogram block, what's that a measure of? That's the mass of the block, falls from a height of 1.0 meters. What is its velocity just before it hits the floor? We're looking for velocity. How in the world are we going to get velocity out of that? Okay? Now, let me back up a moment. Okay? Let's go back to this. Okay? This concept right here. What is the potential energy? This is gravitational potential energy, by the way. What is the gravitational potential energy at the top? What would that be? Is what? MGH. MGH. Perfect. what is when it gets down here and all of its kinetic energy, what is kinetic energy at the bottom? 1/2 mv squared. Okay? Now, let's take those two, and since we know gravitational potential energy at the top is equal to kinetic energy at the bottom, we know that, let's see, which way do we want to do it? Yeah. 1/2 mv squared is equal to mgh. Let's solve that for velocity, because that's often what we want to know. What's the speed at the bottom? Okay? What would be the first thing you do to solve for v? Isolate the v. Divide what? Say again?
V.
Why would you want to do that? You want to isolate the v.
Divide the 1/2.
Okay? Rather than dividing 1/2, I would multiply by 2, right?
Yeah.
Okay, which is the same as dividing by 1/2. So that goes out. So now we have mv squared is equal to 2 mgh. If we're wanting to isolate the v, what would be the next thing we do? Divide by m. I can't write it because, okay, there it is. Okay? But if I divide by m, look what happens. All my m's go out. They disappear. It doesn't matter what the mass is, okay, for this conservation of energy. So now we have v squared is equal to 2gh. But I don't care what v squared is. I want v. So how do we do that?
Square root.
Take a square root of both sides, and that would be v is equal to the square root of 2gh. Why they didn't show that to us on the slide, I don't know, but it is in your book as equation 3.5. Okay? The final velocity, the maximum velocity, is 1/2, is the square root of 2gh. Okay? Now,
I'm still writing. I'm sorry.
okay, let me get that out of the way. Okay? I don't know what this little squibble is over here. Oh, it didn't take. Okay. Okay. Sorry, it's sort of jammed up at the bottom there.
Okay, I'm done.
Okay? Now that we're done with that, let's go on and erase this at the bottom, but remember what we said. In fact, I may not erase it all. Let's just leave that last little formula there. Okay? And what is this asking for here? What is the velocity just as it hits the floor? What would that be? The square root of 2gh. That's the square root of 2. What's g? 9.8 meters per second squared. And your height is 1.0 meters. And this will be square root of, if someone's got it, oh, I can do that in my head. That's 19.6, right? Square root of 19.6. And what units? Meters squared per second squared. And someone with a calculator, I can't do that one in my head. It's going to be between 4 and 5. What will that be? 4.4, what units? Meters per second, because you take the square root of the units as well. So that's a great unit for velocity. 4.4 meters per second. Now, in your book, they made a little error. They put meters times seconds. That's not meters times, it's meters per second. The typesetter got it wrong. Okay? All right. That little formula can save you some effort sometimes. Now, when we're doing it in the lab, you can either use that formula or you can use the one, like, just do the calculations longwise. Okay. Ready for example 310? Still writing? All right, example 310. I'm going to have to erase this one, okay? All right. 310 says, what is the kinetic energy? So here, what we're looking for is kinetic energy of a 1 kilogram book. Why did I erase that? Yuck. Okay, sorry about that. I should have read it first. What is the kinetic energy of a 1 kilogram book? Wait. Let me erase that, sorry. We're looking for kinetic energy. Oh, I don't know what that was. Of a 1.0 kilogram book. What's that? 1 kilogram? That's the mass of the book just before it hits the floor after a 1 meter fall. So it's that very problem we just had. What is the kinetic energy of the book then? Now, I'm going to show you what they do. They do KE. What is the formula for KE? 1/2 mv squared. And we just calculated the V to be 4.4 meters per second squared. Okay? Okay, will someone multiply and see what 4.4 squared is? Excuse me.
19.36.
Say again, 19.7 what? 36. And we're going to take half of that, and that gives us 9.68, which will round to 9.7. What units? Joules. Okay. Now, here's what's crazy about that. What was the potential energy of that ball before you released it? Before it fell? GPE was mgh, which is 1.0 kilograms times 9.8 meter per second squared times the height, 1.0 meters. What does that come out being? 9.8 joules. That should be the kinetic energy just before it hits the floor. Don't go through and come up with a unit, round it off, introduce round-off error, plug it back in, and get this answer and say that's the correct answer. No. The kinetic energy at the end, right before it hit, should be the same as potential energy at the top. So their way of doing it was kind of crazy. It was a lot more work. All you had to do was plug in there, and that kinetic energy at the top should be the same as, potential energy at the top should be the same as kinetic at the bottom. This is where the rounding sort of costs them. Okay? Okay. Now, the next topic is energy conservation, which we will hit next time. But there is a great illustration in the book, since we're still on energy conversion, and that's this one, okay? And this is illustrating what we were talking about before. Energy is never created nor destroyed. It can be converted from one form to another, but the total energy remains constant. And this illustration really does it well. It's a little busy, but it's really there. Start anywhere you want to. Nuclear energy of the sun. It's going on all the time. Probably been going on for about 5 billion years, didn't we say? And it has about another 5 billion years left in its life. Wasn't that about right? In 5 billion years, it's going to burn out, folks. So be ready. No, y'all won't get around. Okay, I won't either. Okay? Now, lots of gamma radiation is given off, but you can also go backwards on it by laser-induced fusion. We won't get into that. But nuclear energy becomes radiant energy, gets transmitted throughout the solar system. Let's just put it that far. That radiant energy can be used to photosynthesize, like right out there in the leaves, and store chemical energy. Or you can burn stored chemical energy, oxidizing things like lighting a fire. That same wood that's being produced out there then could give off radiant energy, both as heat and light. Okay? This chemical energy could go down using electrolysis to be, I can't hold this up, electrical energy, or, the chemical energy in a battery can be used to create electrical energy, or electrolysis moves electrical energy back into chemical energy. Okay? Electrical energy can be used in an electric motor to produce mechanical energy, or by electric generator, mechanical energy is converted to electrical energy. That's what happens at a hydroelectric plant or a coal-fired power plant, any of those. Okay? The mechanical energy here could be produce friction, which produces heat or radiant energy, or a heat engine takes radiant energy and produces mechanical energy. Okay? Or this chemical energy, you burn fuel in the heat engine and produce mechanical energy. That's what our cars are doing, right? Or you can go the other way, and the mechanical energy by friction is producing, it says producing burning. That doesn't make any sense. Back to chemical energy. Or the radiant energy back and forth to electrical. Solar cells go one way, light bulbs go the other way. So all these pathways, every type of energy you can imagine, there's usually a path to and from any other type of energy to produce changing the energy, converting the energy forms. So now let's mark the time. What time is it? 4:28. Let's call it 4:30. So we have had an hour and 15 minutes of class, and when we come back, we'll have another hour and 15 minutes of class, okay, after we finish the lab. So let's pause now, and let me pass out the labs to you.